Alright, continuing with this series of videos, whatever, adding value to Professor Lewin's MIT physics, introductory physics sort of videos. Yeah. So this was, I already saw this because the video had the echo again because I didn't hit the button that stops that. And whatever, so I'm redoing this, and this was a bit of a boring little segment to the very end, so maybe I'll jump a little bit and just to get to the more interesting thing. But anyway, let's continue. Sort of on batteries, and mostly about well, I don't know, batteries and then resistors and then back to batteries, kind of not very coherent.
And I feel this thing getting hot.
Alright, so this
really
was
warming up now.
shorting out the 9-volt battery.
And so I'm ruining this battery. It's a terrible thing to do. Batteries don't like that. But when I take off the external resistance, some of that may come back. It may not be permanently damaged. You see it's already 8.5 volts. So there's no way that you can start a car with a 9-volt Duracell battery, because you just can't get the current that you need for your starter engine. Your starter motor needs a few hundred amperes.
Probably needs more than that, actually, most cars, but whatever. It doesn't really matter, and you need it because of the engine is heavy. You gotta turn it. Motor doesn't really need it, but the motor obviously has to turn the engine, and the engine will need the extra torque.
If you take a car battery, that's about 12 volts. It has a very low internal resistance of about 1/50th of an ohm. So that means that the maximum current that you can draw, if you would short circuit it, would be something like 600 amperes. And so the maximum power, if you were so stupid to short circuit it, that would all be generated inside the battery, would be something like 7 kilowatts. If you ever work on your car, make sure that you never drop accidentally the wrench that you're using onto the battery. Because if you did, then inside the battery, about 7 kilowatts, 7,000 joules per second are going to be produced in terms of heat.
Even back...
And the sulfuric acid is going to boil, the case may melt.
Even back in 2002, most batteries had side terminals, so it wasn't as big a risk of dropping a wrench on them. You know, even so, the old terminals were lead, so even if you dropped it, it was usually pretty easy to break it off anyway. But whatever.
And that's no good. Not only is that stupid, but it's also very dangerous. So let's do it. I have here this battery, and I have here the wrench, just in case. I'm going to short out that battery.
This is like a marine battery. It has little wing nuts on it. You know, you wouldn't find that on a car battery.
And as I do that, you will clearly see that the battery doesn't like it. I will be very careful not to hold on this wrench too long, because it would weld onto it, actually. It can weld onto it and stay there. The current is so high, it can go up to 600 amperes that it can weld onto it, and then you can't get it off anymore. In case that happens, I will walk out of here. And I advise you to do the same.
Yeah, you just take another wrench, give it a little whack, and pop right off. But anyway, it doesn't matter. You can aggrandize with stories that probably only happen like once every 10 years or something in reality.
You ready? Okay, I go now. You see? That's what happens. Very high current. And when you do this too often to batteries, they're not going to live very long. They don't like it. But I wasn't joking when I said when you work on the car that you should avoid this, because I have seen it happen that wrench is actually welded onto the terminals.
I don't know if he's actually seen it, but whatever.
Electric company charges you for energy. They don't care about the power, how many joules you use per second, but they care about how much energy you're using. So they would charge you then for joules, you think. That's energy. However, if you look at your bill, you're being charged for kilowatt hours. Well, a kilo is thousands, and an hour is 3600 seconds. So the units of energy for which they charge you is this in joules. 2000 watt hooking plate, you run for 2 hours, that is 4 kilowatt hours. They will probably charge you 10 cents per kilowatt hour. For that same amount of money, you could run your 100 watt light bulb for 40 hours. Again, that would be the same 4 kilowatt hours.
Electricity is surprisingly cheap. This is the point to be made. It's a lot of energy. Pretty cheap.
Or you could brush your teeth with your electric toothbrush for about $1,000.
I mean, if you made the comparison to how much labor you would have to do, physical work, turning butter or something, or whatever, doing work, it would be like a preposterous amount. Like you'd have to spend all day turning some wheels or something just to make, 10 watts of electricity. So
now I want to take a look with you at a network which consists of resistors and batteries.
I think I'll speed this
is the
up.
kind of stuff that you see on homework assignments,
Because
and
this is a bit.
on
I've
exams.
already been there, done this.
So now we start out with a very modest circuit. Here we have a resistance R1. Here we have a resistor R2. And here R3. And then we put a battery in here. And we put the plus side, say, on the left, the plus side, the minus side, and let the potential difference of this one be V2. It's really the EMF, but I will ignore any kind of internal resistance of the batteries. It's completely negligible in this problem. And here I put also a battery, let this be the negative side, and this be the positive side, and let the potential difference be V1. And so imagine that you know V1, V2, R1, R2, and R3.
Alright, so the V1 and the V2 are totally superfluous. They're two batteries in parallel. So you could just eliminate one of them. Just put a straight line right through it, and you'd have the same circuit. So for whatever reason, he decided to do this so he could do his trick. I just don't think it's a very interesting trick. Go ahead.
But what I'm going to ask you is, what is I1, what is I2, and what is I3? I want the magnitude, and I want the direction. When you look at this, it's by no means obvious that the current in this resistor will be to the right or to the left. It's by no means obvious. It depends on the values of V1 and V2 and on the resistances. The basic idea behind solving these problems are in what we call Kirchhoff's rules. Kirchhoff's first rule is that the closed loop integral over a closed loop of E delta L is 0.
The real trick is you have to have if you take one of the batteries out, you have to jump that line over to the negative side. So let me just get to the drawing.
We've seen that before.
Then I can
I don't know why
point it out.
Kirchhoff gets the credit for this. This always is the case when we're dealing with...
Right, so it's all kind of obvious. There's this idea that the whole circuit has to come out to 0. So you go from a positive end to the negative end, and your net progress is 0, going through the whole cycle. And so what I'm saying is the far negative post of the battery, the R1, just has to be jumpered to the R2 side, which really wouldn't make any sense. You'd have to, I don't know. So I guess that's why he's got two batteries in, is to create a very small resistance, not to make these two resistors just in parallel, but essentially R1 and R2 are in parallel, essentially. So it's just two resistors in parallel on one side and one resistor on the other side. So it's just a two resistor equation. And he's arguing that doing this two resistor equation instead of the three, but he does it in drawing.
conservative fields. When you start at a particular point, you go around E delta L, you're back at the same potential where you were before, so this must be 0, as long as you deal with conservative field. But that's his first rule. And you can do this closed loop anywhere. You can even do it here. It'll still be 0. You can do it here, also 0. You can do it there. No matter where you do it, that closed loop integral must be 0. And then there's the second Kirchhoff's rule, and that is what we call charge conservation. If there's a steady state situation, then independent of which junction you go to, the current that flows in must flow out. Can't have a pile-up of charge. That's the second rule. And I gave you a problem, 3.7, to work out, and you can look in the book how that is done. However, I'm going to work on this with you in a slightly different way than the book is doing it, which I personally like better. But it may confuse you, so I warn you in advance. You may not want to use my method at all. What I do is the following. I say, okay, I assume that there is a closed loop current here, I1, and that there is a closed loop current here, I2. Whether I make them clockwise or counterclockwise, unimportant. I could have.
Okay, so it is sort of important because now he's going to have to combine the two wheels and this is going up and this is going down. He's going to have to do all that stuff. So he basically drew one current going from negative to positive and the other current going from positive to negative, creating, in my opinion, a complexity you just don't need. If you just would have drawn the other one going the opposite direction, then they both then the obvious would have been true, which is you're always going from high pressure to low pressure, not low pressure to high pressure. So he just creates an inconsistency here that just makes it more complicated, I think. And so yes, I would go with the book.
Choose one clockwise, the other counterclockwise, unimportant. However, once I choose a direction, it has consequences, as you will see. And that's all that's running. One current like this, and one current independently like that. If I assume that, then I have automatically I am obeying the second rule, because a current that goes around, there's charge conservation, right? There's no charge piling up. So the second rule of Kirchhoff is already obeyed. So now I go to the first one, and I can start now at any point in that circuit and go around. I can go around clockwise, I can go around counterclockwise, it makes no difference as long as I return to the same point. That integral E dot L must be zero. I'm return.
It does make a difference, but it has to do with these plus and minus signs and getting them right. Whatever.
At the same potential. What is the integral of E dot dl in going from point 1 to point 2? Well, that's the potential difference between point 1 and point 2. And so let us start here, and let us go around. And we have to adopt a certain convention, namely, if you go up in potential, we go down in potential. Again, you're free to choose the sign convention, but I would say when I go up in potential, I give that a plus sign. When I go down in potential, I give that a minus sign. So I start here. I could have started there, I could have started there. It makes no difference as long as I don't start here. That makes no sense. So I start here, and I go around like this. So right here, I go down in potential, V1. So I get minus V1. Now I go with current I1 in the direction from left to right. So that means that the potential here must be higher than there. V equals IR. Potential here must be higher than there. So I go down in potential, so I get minus I1 R1.
So he's going by his pink arrows to define what low and high is, instead of going by the actual circuit, which, again, the two circles he's drawn are opposite conventions. One is spinning, plus to minus, and one spinning plus to minus to plus.
Now I go to R3. This current I1 is going down, so this has a higher potential than here, so I go down in potential, so I get minus I1 times R3. But I have independently a current I2, which is now coming towards me when I go down. And so if it comes towards me, that current will give me an increase in potential. This would have to have a higher potential than this for this current to do this. So now I climb up the potential hill, so I get now plus I2 times R3.
All right, well, I think I'll just skip some of this, but, he's basically going to argue that he's only doing two equations where you'd have to do three the other way. But see, he just did a third equation. He's just putting the third equation in the two equations, because now he's basically, he was doing one loop, and now he's putting in a factor for the other loop's effect on the first loop. And so he's just adding functions that he wouldn't have to add if he had the two loops going in the same current direction. So just kind of, whatever. I don't think very clever. So I'll jump a little bit ahead here.
2. Now 0. Two equations with two unknowns. I can solve for I1 and I can solve for I2. So I1 and I2 pop out. Let us assume that I1 is positive. I find a positive value. It means it's really in this direction. Let's suppose that I1 is negative. I find minus 3 amperes. Well, it means that I1 is in this direction. Big deal. And so the whole operation is sign sensitive. And the same is true here. If I2 is positive, it means it's in this direction. If I2 is negative, then it's in that direction. How about I3 now? Well, let us assume that I1 is plus 3 amperes. And that you find that I2 is plus 1 ampere. That's possible, right? You have two equations, two unknowns, and these are the answers. So 3 amperes goes like this. down, and 1 ampere comes up. Well, it's clear then that I3 is 3 minus 1 is plus 2. Another way of looking at it is 3 amperes come in at this juncture. I2 is 1 ampere, so 1 ampere goes through, so 2 must go down. That's really Kirchhoff's second rule. If I1 were plus 1 ampere, and I2 is also plus 1 ampere, then I3 would be 0.
Right, but it has to be 2 because the two resistors are essentially in parallel. So again, I don't think this saves any calculating work. I think it would be better just to obey the convention of having taking the path that's always from high to low, not arbitrary paths.
I know some of you don't like it, it's fine. The reason why I like it is I always end up, in this case, with 2 equations with 2 unknowns. I solve for I1, I solve for I2, and then the third one comes out in a natural way by just thinking, one current goes in this direction and the other goes in that direction. But if you prefer the method that the book will present to you, you get 3 equations with 3 unknowns. And
so he's just saying 3 equations, and since you have 3 I's for each of the resistors, so there's the 3 equations, and he's just basically putting the middle resistor into the R1 and the R2 equation. So it's the same amount of little piles of crap. So whether there's 3 equations with fewer functions or 2 equations with more functions, what's the difference?
You get I1, I2, and I3 right at the start. You get an I3. You see, I don't even start off as an I3. It's not there. It comes in later. So the choice is yours. Now I want to entertain you for the last 6 minutes with something amazing, something that is truly amazing, and it is a form of a battery that is mind-boggling. And the battery is right here on my left, on your right.
Yes, pretty cool. First time you see it, you say, yeah, that is neat. Yeah.
It is a battery that produces an enormous potential difference. 10, 20 kilovolts. You see a schematic here on the transparency. You have a bucket of water here on the top, and you have glass. And the bucket of water is hiding behind here. Not that because we hide it from you, but that's the best place to be. And you see plastic tubing coming down, and the water can run out on the right, and it can run out on the left. It runs out here. There is some paint can, no top and no bottom. And you see this paint can here, it's completely open, it's the letter A. And there's another paint can on the right, it's the letter B. It's a conducting can. It is also a conducting can. And this water runs into another conducting trash can. And this water also runs into a conducting trash can. Now comes a key point. That this conductor here, A, is connected through a conducting wire with C, and the conductor B, the paint can, is connected with a conducting wire through this trash can D. You let the water run for a while, and you will see between these 2 points here, sparks. Even when the points are as far apart as, say, 5 millimeters, when you're talking about at least the potential difference of something.
Yeah, so it's another one of these experiments that would be very interesting to see it reformed in different configurations, like instead of using buckets at the top or things that are encompassing the water, whether you could just use a flat plate or some different things, because I believe you could, because part of what's happening doesn't really it's a little, the can is deceptive because it might not be necessary, but anyway, but yes, it would be it's a kind of experiment worth playing with to see what ruins it and what perhaps makes it work better and worse.
Like 10, 15,000 volts, you will see the spark. And you wait, see another spark. And you wait, and you see another spark. So this is a power supply. There must be energy coming from somewhere. And so problem 4.1, which you haven't seen yet on your 4th assignment, is asking you how this works.
So the energy is gravity, but the function is friction. So water molecules don't like being broken apart. And and then they're moving through the air, and so those 2 factors, breaking their adhesion, and turning them into drops, and them dropping through the air are the 2 things causing the charge.
I will demonstrate it today, and I will come back to it later. The way it works is actually quite subtle, but I want you to think about it. It's a remarkable battery, a remarkable power supply. As the water starts running, I want to draw you.
That's data. I've seen it before, so I know something about how it works. But I might be saying things a little differently than he would put it, certainly. But he's not going to be putting it in this video. So that'll be a future video where more details are provided.
Attention to the fact that you can almost anticipate when the spark occurs. Because the water, at the very last, is beginning to spread. It doesn't come out anymore just like a narrow cylinder, but it begins to spread. And then comes the spark. And then it goes back to running normally, and then slowly in time.
Right, so it starts to spread as the voltage starts increasing. So the voltage is increasing in the bottom bucket, and that bottom bucket voltage is being sent to the top can, which is now becoming charged at 10,000 volts, which is creating the magnetic effect of pulling the water, because the water is obviously opposite charge.
It will spread, and then comes the spark. So let us get it going. We have some light here. Marcos and Bill spent a lot of time getting this going. Marcos, do you have all my lights the way you want them? You're happy with that. There you see the two balls, which are really here. And let's first look at the sparks. So I will start the water running now.
So this has almost got a little bit of a Tesla thing to it. You know, by narrowing the gap, if you made the gap smaller and smaller and smaller, you'd have a lower voltage that you know, neutralizes, you know, puts the system back to ground. And so it would cycle quicker, and spark, 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 which might be more interesting. But anyway.
Let's just be patient a little bit. And let's see where we see the spark. Did you see one? Did you see the spark?
No.
Oh, you were not looking. Man, you're paying for this. Look at the two balls. Give it some time again. You have to charge up. I can already anticipate it's coming up. Coming up. Yeah. Did you see it?
Nope.
15,000 volts. Let's give it a little bit more time, and then we'll take a look at the water flow.
It's just the frame rate issue. So if I played the video again, you might see the spark, but not this time.
Which I can see. It flows. We can make you see the water flow. Look again. It's coming up. Did you see it? I can see it coming up. I can make you listen by having my microphone near the water. You can hear this water running. Really, the sound all of us. And now the sound changes. You hear change? And there's the spark. Once more. It's running. Spreading. Coming up.
So as the say the bottom bucket's getting the charge, it's sending the charge to the B can. The B can is now getting whatever 7,000 volts, and so it's becoming quite charged and causing the ionized water to move towards the outside of the bucket.
Yeah! Amazing, isn't it? I can make you see this water. Just stay there. We have 1.5 minutes left. So now you can see the water. You're happy with the light, Marcos? You can improve on it. So look at the water. It was just spreading already. You can't see the spark and the water at the same time. See, the water is running now normally. It's going to spread slowly. I will tell you when I see the spark here, but it's already, I can almost predict when it happens. The water is spreading now. Coming up shortly. Yeah, I saw the spark. And you immediately see the water go like this. I want you to think about it and explain this. This is one of the most remarkable things I've ever seen in my life.
Alright, so I might have explained it wrong, actually. I mean, I think the charge on the bucket has to have something to do with something, but obviously the inside of the bucket's not supposed to have that much charge. But it seems like it does. But the water molecules themselves might be getting more and more charged, so they're separating more. But again, where else going to get charge from but the can? So, but anyway, we'll wait till the future video to nitpick over details. Such. Alright, so that's it. Alright, so not terribly interesting stuff to work with, but we'll endeavor to persevere. And, you know, there will be more interesting things to come, no doubt. And such. So, till the next time.